Let's talk about calculus, specifically that one part that feels like pure memorization, trig derivatives and integrals. But what if I told you there's a better way than just cramming? We're going to build some real intuition and unlock a hidden pattern together. Let's get into it.
So, have you ever felt like learning calculus is just a huge, frustrating memory game? Because if you have, you are definitely not alone. It can feel like you're just trying to stuff this endless list of formulas into your head, right? Especially with trig stuff. But what if I told you it doesn't have to be like that at all?
Okay, so you see a chart like this, and yeah, it's totally normal to feel your brain just short-circuit a little. I mean, look at it. 6 functions, and each one has a derivative and an integral. So that's what, 12 different things you have to memorize? Well, no. The secret here isn't about memorizing 12 things. It's about understanding one simple, really powerful pattern that's hiding in plain sight.
And that powerful pattern? It all boils down to one core idea, the concept that differentiation and integration are what we call inverse operations. Think of them as two sides of the same exact coin.
So what exactly is an inverse operation? Well, it's pretty simple. Think about tying your shoes. That's one action, right? The inverse action is untying them. It perfectly undoes the first thing you did. We see this all over in math. Addition and subtraction, they're inverses. Multiplication and division, yep, inverses too. One operation builds something up, and the other one tears it right back down to where it started.
Now, in the world of calculus, our two big players are differentiation and integration. Differentiation, that's all about finding the rate of change. You know, the slope. It's asking, hey, how fast is this thing changing right now? Then you've got integration. That's about accumulation, finding the total area under a curve. It asks, okay, how much stuff has piled up? They sound pretty different on the surface, but you're about to see they're actually perfect opposites.
Okay, let's actually see this inverse idea in action. And we'll start with the most famous pair in all of trigonometry, the sine and cosine dance. This is where that hidden pattern is going to become crystal clear.
All right, check this out. This shows the whole round trip. Look at that top row. We start with sine of x. We take its derivative, and what do we get? Cosine of x. Simple enough. Now let's do the inverse. Let's take the integral of cosine of x, and boom, we land right back where we started at sine of x. See that? It's a perfect loop.
So here's the key takeaway. You don't need to memorize 2 separate facts here. You just need to know one thing. Sine and cosine are partners. Differentiating one gets you to its partner, and integrating that partner brings you right back home. They bring you full circle. And you know what the best part is? This isn't some special one-off trick that only works for sine and cosine. Nope. This exact same pattern is the key that unlocks all the other pairs on that scary-looking chart. Let's see how. Okay, take a look at tangent and secant. The derivative of tangent of x is secant squared of x. So let me ask you, what do you think the integral of secant squared of x is? You got it. It's tangent of x. It has to be. And it works for secant too. Its derivative is secant of x times tangent of x. So when you integrate that, you get right back to secant of x. It's the same exact round trip, just with a different set of dance partners.
This is it. This is the whole idea. You can finally stop thinking of that chart as a long list of 12 random, disconnected facts you have to memorize. Instead, you can see it for what it really is, a list of 6 pairs of partners, and for each pair, the rule is simple. What differentiation does, integration undoes.
Okay, but if you're paying really close attention right now, you might have a little question nagging at you. You might be thinking, hang on, what's the deal with that little plus c that keeps popping up every time we integrate? Let's talk about that. And that's an absolutely fantastic question. I mean, if there's such perfect inverses, if one just undoes the other, why do we have to tack on this mysterious plus c at the end of every single integral? What's it for? Where does it even come from?
All right, here's the simple answer. Let's think about a function, say x squared plus 5. What's its derivative? It's 2x. Okay. Now, what about the function x squared plus 50? Its derivative is also 2x. You see, the derivative of any constant number is just 0. It vanishes. So, when we differentiate, we lose any information about a constant that might have been there. Integration is smart, though. It adds back that plus c. We call it the constant of integration, basically as a placeholder. It's saying, hey, there might have been a number here, and we don't know what it was, but we're accounting for it.
So now that we get that, we can officially throw out that old, painful memorization strategy.
we can replace it with a much smarter, way more intuitive approach to really master these things.
Here's your new game plan. It's just 4 simple steps. Step 1, identify the function you're working with. Step 2, find its partner on the chart. For tangent, the partner is secant squared. For secant, it's secant times tangent. Step 3, just remember the inverse rule. Differentiating goes one way, integrating goes the other. And finally, step 4, and this is important, if you're integrating, always add that plus c to cover for that lost constant.
So look, the big takeaway today is this. Stop trying to memorize a long list of separate, isolated facts. Instead, start understanding this beautiful, interconnected system. Because once you really see the pattern, once you see this dance between inverse operations, the need to just memorize stuff, it kind of just melts away.
And that's really the core idea. Once you see this deep inverse relationship here in calculus, it leaves you with a really cool question to think about. What other things in math or even in science that we learn as separate rules are actually just two sides of the same coin? It's a totally different and way more powerful